Welcome to Shri Learning Academy. Let's simplify hardware solutions to synchronization. We've already seen how hardware can provide powerful atomic operations for synchronization. If you've watched the earlier chapter on atomic instructions, you already know how test and set works as a basic locking mechanism. So instead of repeating that foundation, let's move forward and look at two other important ideas from the hardware side of synchronization: the swap instruction and memory barriers. One helps processes exchange control safely, and the other ensures operations happen in the correct order. Both are extremely important in modern concurrent systems, even if they often remain invisible to normal users. Let's begin with the swap instruction, sometimes written as XCHG on some processors. Unlike test and set, which checks a value and then locks it, swap follows a simpler philosophy. It performs an atomic exchange between a CPU register and a memory location. Atomic again means indivisible. No other thread or process can interrupt halfway through the operation. The exchange happens as one complete action, which is exactly what makes it useful for synchronization. To understand it clearly, imagine a small token box placed on a table. That box represents a shared lock variable stored in memory. If the box contains a green token, represented by 0, the resource is free. If it contains a red token, represented by 1, the resource is busy. Now, every process that wants access arrives carrying its own red token. When it attempts to enter, it performs a swap. In one instant move, it exchanges its token with whatever is inside the box. Now the result tells the whole story. If the process pulls out the green token, it means the box was free. It has successfully claimed access, and the box now contains the red token to signal everyone else that the resource is occupied. If the process pulls out another red token, it means someone already owns the lock, so it cannot enter yet and must try again later. This is synchronization through exchange. No guessing, no partial steps, and no dangerous timing gap between checking and updating. Let's make this practical. Suppose two threads want to update the same shared file record. Thread A performs the swap first and receives the green token. That means it now owns the lock and can safely update the file. Thread B performs swap moments later but receives red. So it knows the lock is already taken. It waits and retries later. Once thread A finishes, it releases the lock by writing 0 back into the shared variable. Then thread B may succeed on its next attempt. This is how mutual exclusion can be enforced using a very small hardware instruction. You might now ask whether this is similar to compare and swap, which we discussed earlier. They are related but not identical. Swap is unconditional. It does not check whether the memory value matches anything specific. It simply exchanges values every time it runs. Compare and swap is more selective. It only changes the memory value if the current value matches an expected value. That makes compare and swap more flexible, especially for advanced lock-free data structures such as stacks, queues, and reference counters. Swap, on the other hand, is simpler and often very fast. Because of that simplicity, it has historically been useful for implementing basic spin locks and low-level kernel synchronization. In many systems, the operating system relies on these primitive instructions to build higher-level synchronization tools. So even if developers today often work with mutexes or semaphores, the hardware underneath may still be using concepts like swap. Now let's move to something less visible but equally critical: memory barriers, also called memory fences. We talked about it in the Peterson's algorithm video. Now let's understand why they matter. Remember that modern CPUs are designed for speed. They do not always execute instructions in the exact written order if they can optimize performance. They may reorder reads and writes internally, use caches aggressively, or delay when updates become visible to other processors. In a single-threaded program, this usually causes no problem. But in concurrent systems, it can create serious bugs. Imagine one thread updates shared data and then releases a lock. You would expect other threads to see the new data after the lock becomes free. But a smart CPU might reorder operations so the lock release becomes visible first, while the actual data update is still delayed. Another thread sees the lock as free, enters the critical section, and reads stale data. Everything looks correct in code, but the result is wrong in practice. This is one reason synchronization can be tricky on modern hardware. A memory barrier solves this by acting like a checkpoint. It tells the processor that all memory operations before this point must be completed and made visible before operations after this point can continue. In simple terms, it says, stop here. Finish earlier memory work first. That creates predictable ordering between threads and processors. Think of it like workers building a wall. You cannot paint the wall before the bricks are properly placed. If workers rush tasks out of order, the result fails. A memory barrier is the supervisor ensuring the correct sequence. First place the bricks, then inspect, then paint. In computing terms, first write shared data, then release the lock. The order matters. This becomes especially important in multi-core processors where several CPU cores may each have their own caches. One core may update a value, but another core might still see an older cached copy for a short time. Memory barriers help coordinate visibility so processors agree on what happened and when it happened. Without them, synchronization code that looks perfect may still behave unpredictably. So when we step back, we can see the full picture. Software algorithms like Peterson's algorithm taught us the logic of mutual exclusion. Hardware instructions like test and set and swap gave us fast atomic building blocks. Memory barriers then added ordering guarantees for modern processors that aggressively optimize execution. Together, these mechanisms make real-world synchronization practical, scalable, and reliable. These are the raw construction materials of concurrency. In the next chapters, we move from bricks to buildings. We'll see how operating systems use these low-level hardware tools to create user-friendly synchronization primitives like semaphores and mutexes, which developers use every day without always realizing what powerful machinery exists underneath. That is it for this video. See you in the next one.